All right, guys, so we're looking at the calculus involved with parametrized curves and keeping track of some of those big issues that we had from essentially Calc 1. And the next one we want to look at is area under a curve. So again, we're looking at the area under this curve. Move myself here. We're looking at the area under this curve. But remember, the curve is given by parameterizations for x and y, right? Each of these curves is going to be parameterized. So we're treating x and y as individual functions of some parameter, in this case t. And again, I like to think of t as kind of like time. So here's a situation. We've got this integral from a to b of y dx equals an integral from alpha to beta of g of t f prime of t dt. Well, if you think about Calc 1, right, it's kind of a standard problem. Let's say there's a curve. If you've had me before, you know that's my favorite curve right there. It's my go-to. You got a to b, and then we've got this area, okay? Now, we're trying to find the area under this curve, and we know that, especially if this curve is given by y, we know that the area is the integral from a to b of y dx. Okay, this is a very basic sort of fundamental problem that you might see as an introduction to the definite integral. But remember, y is actually g of t, right? And x is actually f of t, okay? Well, if x is f of t, then, whoops, dx is going to be f prime of t dt. So you essentially have this change of variable, right? And we also know that x of a is going to be alpha, and x of b would be some beta, right? These are t values. So this integral with a simple substitution, much like a u substitution, just becomes the integral from alpha beta g of t f prime of t dt. Again, g of t is y, and f prime of t dt is dx, okay? Let's see how this plays out. So the next problem, actually I'm gonna get rid of a little bit here. Let me see. Okay, so sorry I had some writing over this. Let's take a look at this. The area enclosed by the curve over the interval 0, pi. So what do we mean by that? Well, we know that then t, right, ranges from 0 to pi. Okay, we also know that the area is going to be the integral from 0 to pi, and then we have y, which is 2a sine t minus a sine 2t times, right, this is y, times the derivative of x of t, right? So let's see, 2a cosine t. Derivative of cosine is negative sine. So we have a negative 2a sine t. And then a little chain rule over here will give me plus 2a sine 2t dt. Okay. Again, this piece is my dx, all right? And I'm not gonna have you sit and watch me work all this out, but using some trig identities, it's actually comes out kind of nice. It's negative 3 pi a squared, which is kind of surprising, but there we go. All right. The other issue is surface area, right? You have some curve and you want to revolve it or rotate it about the x or y axis. That generates a volume, but that volume is bounded by some surface, right? And that has an area. Dissecting these, right, we remember that essentially we had this 2 pi and then times f of x and then times arc length, right? Well, didn't we show that this is just arc length? So essentially this is the parameterized version of arc length in our previous surface area problem, okay? So should be pretty straightforward. So let's see how this works. So surface area generated by revolving x equals cosine t, y equals 2 plus sine t, from 0 to 2 pi about the x axis. So I've got this equation, and while I'm at it, I'm going to find dx dt. And so dx dt will be what? Well, negative sine t. And then my dy dt will be what? Well, cosine t. Okay. And so my surface area integral becomes the integral from 0 to 2 pi of 2 pi y, right, which is 2 plus sine t, times negative sine t squared plus cosine t squared. And dt. Now, how nice is this? Gotta love it when this happens because that's just 1. And so what do we have? Well, we have 2 pi times the integral from 0 to 2 pi of 2 plus sine t dt. So what do we get? Well, 2t, and then antiderivative of sine is going to be negative cosine, so minus cosine t from 0 to 2 pi. Well, let's see, 2t, so that 2 pi is going to be 4 pi minus 1 minus, and then plug in 0, we get 0 minus 1. And so let's see here, negative 1 minus negative 1. So what are we going to be left with? 8 pi squared. That's all said and done. Okay. All right, let's try one more. Surface area generated by revolving this guy about the y-axis. So again, before I start, I'm going to come in here and find dx dt, which is, let's see, 3/2 times 2/3, that's just 1. So t and 3/2 minus 1 is 1/2. And dy dt, well, that's like 2t to the 1/2. So it looks like we get t to the negative 1/2. Okay. And so I'll have the integral from 0 to the square root of 3, 2 pi times, and then 2/3 t to the 3/2 times the square root. And then we're going to square these guys, right? T to the 1/2 squared plus t to the negative 1/2 squared. dt. And let's just see what happens here. So I'm going to have a, let's see, 2 pi times 2/3. So 4 pi thirds integral from 0 to the square root of 3. And then we've got, let's see, t to the 3/2. Let's see here. Right, to the 3/2. And then what does all this become? Well, t plus, let's see, 1 over t dt. And let's see if good things happen here algebraically. Dare I say, moral things happen. See, if we were all in person right now, we'd be having a good laugh. All right. So now, all right, so let's see. My radical will become, get a common denominator here, t squared plus 1 over t dt. And I'm thinking nice things are going to happen. So I'm going to have a 0 to root 3. I'm going to have a t to the 3/2, a square root of t squared plus 1, all over a square root of t dt. If I come up here, we'll have our 4 pi thirds. Let's see, t to the 3/2 over t to the 1/2. Ah, that's just t. T squared plus 1 dt. This is a little u substitution here. So du is going to be 2t dt. U of 0 is 1. U of root 3 is going to be 4. And so let's see, we have a 2t there. So this is going to be from 1 to 4, 1/2, and then square root of u to the 1/2. So we're going to get a 2 pi thirds. And then u to the 1/2 will be what? Well, 2/3 u to the 3/2 from 1 to 4. And so we get 4 pi 9ths. And then u to the 3/2. So 4 to the 3/2 minus 1 to the 3/2, which is just 1. And so 4 to the 3/2. Well, 4 to the 1/2 is what? 2. So 2 cubed is 8 minus 1 is 7. So we have 28 pi over 9. Okay? So there we have it. Those were our last two applications of calculus with parametrized curves here. We looked at surface area. We looked at area under a curve. So again, make sure you go back through and rework these and make sure that you're also working some homework problems. I think that pretty much covers this section. And so where we're going to go next is looking at polar functions and polar coordinates, and then the calculus involved on functions and polar coordinates. So make sure you spend some time with this parameterization. You want to be comfortable. And then when we move to polar coordinates, I'm going to do a nice big review of things you should have seen in pre-calc. If you took pre-calc at our college, then you definitely did. And then we'll get into the calculus of it after that. All right. Hope all is well with you guys. Keep up the good fight. Stay safe. Stay healthy. And appreciate all of your efforts as we move into this turbulent time. So I'm here for you guys. If you need anything, just let me know, and I'll be with you.